So last time what we did was we saw how we could integrate our equations of motion. Then we learned how to look for another constant of motion. We learned that the possibility exists that if you have a constant in addition to the Hamiltonian that doesn't change along the trajectory, you could actually then have your four-dimensional phase space. The Hamiltonian restricts it to a volume in the four-dimensional space. If you have another restriction or another constant, it would be restricted to the surface in a four-dimensional space. And then what would happen is if you took a section through that, for example, z equals to z0 equals to a constant, and you were to plot p rho against rho, then you would get your closed curves, which then would be the verification that you had the correct second constant, so that a second constant existed. Once again, if you got closed curves, it wasn't proof, but it was at least necessary for the second constant to exist. In other words, if you didn't have this constant and you got a random scatter, you would definitely know you didn't have it. Okay. So this possibility of finding another way to describe the trajectories beyond just the equations of motion is what I did the last time. And what I want to do today is formalize it a little bit further, as well as finding a way to go looking for it. Okay. And that is in some sense the aim of Hamiltonian mechanics, is to try and take your original system and then transform it to a system of coordinates in which the integration structure is obvious. In other words, your system of coordinates in which you have one coordinate that labels your trajectory and another one that tells you how you're moving around it. Okay. So just to actually go further, the idea of a constant of motion, and I see my screen has lost the... It's the cable that's losing the red. Okay. Oh well, we've just lost the red on screen. Anyway, the idea of a constant of motion is the second quantity q, so let's call it q, that doesn't change along the trajectory. So we simply write it out as q dot is equals to 0. And what that basically means is that Q commutes with the Hamiltonian, okay? So what I'm going to do now is also start transitioning from partial differentials and time derivatives into using the Poisson brackets. And I'm going to do it slowly because it's the Poisson brackets then let people go further to develop quantum mechanics and a number of other systems. So all I want to simply prove to you now is simply if we have this thing that's constant, in other words, we have some function of q and p. In two dimensions it's like 4 variables, in higher dimensions it's more, and it doesn't change along the trajectories, then it commutes with the Hamiltonian. And the way that you work that out is simply if you have any function of coordinates and momenta, you work out f dot, you simply use your chain rule. You take df dq times q dot, and you do this for all possible q variables, plus df dp times p dot, okay, and you're summing over all possible momenta over there, and then you've got a complete expression for what f dot is. And if q dot and p dot obey the Hamiltonian equations, you can simply use that to replace them, and you're left with q dot being dh dpk, remember it's different, they cross, minus df dpk times dh dqk, and so this is your exact definition of your Poisson bracket. Okay, so it's just straightforward application of your definition as well as the equations of motion, and knowing that the equations of motion come from a Hamiltonian system. And therefore you have that for all f, you can always express f dot equals the Poisson bracket or the commutator of f with h, and therefore if f is a constant of motion, Q, we know that Q dot is equals to 0, and therefore Q, the Poisson bracket of Q with H is equals to 0. Okay. So what I'm going to do for this lecture is simply start building up the framework where we actually want to transform into variables in which you have as many things commuting with your Hamiltonian, in other words, df dh equals to 0 as possible. And the way I'm going to do that is as follows. So I'm going to define what we call a canonical transformation, right? So what we could in principle do is say we start with some little q and we change all the position coordinates, okay? But if you do that, you're automatically going to change the differential equations for the position, and you're no longer going to have this thing that you can get a Hamiltonian so that you can get q dot equals dh dq and p dot equals dh dp, because you would have mixed up your variables. So there's a very special type of transformation where you change not just the position variables, but both the position and the coordinate variable, both the position and the momenta variables, so that you retain the structure that you can always derive the equations of motion from the Hamiltonian. Okay, so, and that we call a canonical transformation. So a canonical transformation is a transformation that takes the original set of generalized coordinates q and p, so position and momenta, and it generates a new set of canonical coordinates that we're going to call them big Q and big P, in a manner that performs the Hamiltonian, that preserves the Hamiltonian form of the structure. So we still want this nice thing that in our new variables we're going to be able to derive the equations of motion by taking the derivative of some function in the structure that we've done it in the past. And the questions that then come up are basically, how do you specify the transformation that preserves the structure? In other words, what restrictions are there in the changes of variables that make this possible? And the second question, so I'm going to try and answer the first one today. The second one is, for a given Hamiltonian H, can you find a transformation which makes all the Qi ignorable? In other words, can you find a transformation where all the variables behave roughly like our t and phi coordinates that makes it very easy to integrate this stuff, and therefore we've got one coordinate that labels the trajectory and other coordinates that just run along it, but it's a very, very simple structure. And generally, if you found this the transformation of the Hamiltonian to the set of very special coordinates, then you consider your problem to be solved or integrated. Okay, so in some sense, that's the formal aim of Hamiltonian mechanics. And so what I'm going to do today, I really would like my colors. It took a lot of effort to put the colors in. Is actually just answer the first question and then start building up the infrastructure for the second one. Okay, so if you want a place to go look this up, and quite a lot of this what I do today comes from Goldstein chapter 9. In fact, they have a number of useful examples and a number of other tangents that they also go on that would be worthwhile reading through as well. Okay, so, but if you want examples to illustrate further what I've done, this is where you go hunting. Okay, so let's simply take the stuff on the right and actually write it down in equation form. So suppose we have an n degree of freedom Hamiltonian, in other words, k goes from 1 to n. We write down our equations of motion, and in the one set of variables, and then we have the second set of variables, a transformation to a new set of variables, which we're going to say our big variables are q, which are functions of the previous set, namely qi, p, or qj, pj, and the big P is also a function, a different function of qj, pj. So here you basically, what you've done is specify two n equations, right, for P and Q that have all the content of your transformation in it. What I'm also going to do is I'm first going to do it with respect to partial derivatives and then actually show you what the results mean for the Poincare brackets. Okay, so first I'll stick to what I initially felt more comfortable with to compute, which is the partial derivatives, derive the results, and then I'll show you what it actually means in terms of Poincare brackets, which is what people then went on to generalize to get quantum mechanics. Okay. It's actually quite interesting. If you look at like the two major branches of physics, the relativity people took Lagrangians, which is related to this, and they generalized that to make measurements in geometry. And the people that did quantum mechanics took these structures that come for the Poincare brackets and generalized that to make quantum mechanics. So it's sort of split into two branches from the Hamiltonian mechanics using two different formalisms. And those two branches have never, in fact, the whole reason that we start looking at the orbits around black holes is that's where the two branches don't agree, right? There's a contradiction between quantum mechanics, a very fundamental one, and that you'll hear later on, between quantum mechanics and relativity at black holes and at the Big Bang. So those are the places where they actually they're not consistent. They make predictions that are contradictory, which is why there's so much being poured into testing GR, and they're building satellites and things to actually do it. It's because there's a fundamental question they want to answer. Okay, so now the transformation is canonical if there exists a k, some other function of your transformed variables q and p, such that the equations of motion, basically q dot can be written as dk, dpk in the new variables, and p dot can be written as minus dk dqk. Okay, so there's our Hamiltonian structure in the new variables. That's the same as the structure in the previous variables, but possibly with a different k. So that's our definition of the most generalized canonical transformation. What I'm going to do is I'm going to look at a class that they call restricted Hamiltonian transformations, because it's slightly simpler to do the analysis for them, and it's also the only ones we're going to need. So for this class, and so I just want you to know that there's a slightly more general class, Goldstein discusses it, but we're only going to look at the restricted ones. So the restricted one says, let us look at k, which is a function of the new variables. We can then write k as a function of the new variables, which are in themselves the functions of the previous variables, the small ones, q and p. Okay, and then if this k that's now basically been written as functions of the original variables is equals to the original Hamiltonian, that's a restricted transformation. Okay, so it's just, you know, the advantage is that you know exactly what k is, both in the original variables and in the new variables. Okay, so we're going to look at those classes of transformations, in other words, transformations like this that result in your new Hamiltonian where the structure is obeyed and the new Hamiltonian in the new coordinates in value is equals to the old Hamiltonian in the old coordinates. And we're going to work out the consequences of that and what that restrictions actually places on these two inequations, so that we can actually get it out. So to do that, I'm going to say let z be equals to, I'm going to combine all my variables into one, basically one vector. So I'm going to say z is going to be a vector where I have all my q's stacked on top of each other, and then when I've run out of my nq's, I'm going to stack all my p's, and then I'm going to have this big Z be such that basically represents my new variables, all the q's, and then all the p's stacked on top of each other. And so each of these things or vectors basically have two n components. And now what I'm going to do is I'm going to make a different matrix, which I think some of you may have come across. I'm going to call this matrix J. And what J is simply the 0 n by n matrix followed by an identity n by n matrix, and you have minus an identity n by n matrix, and you have 0. So this is a 2n by 2n matrix, and J is designed to try and give me the structure where I have decay dp, that q dot is equals to k dp, and p dot is equals to minus decay dq. Okay, and so what I'm basically going to do is use these two things to rewrite my Hamiltonian equations in the following way. So I can say z dot, in other words q dot and p dot, is simply j times the gradient of h with respect to z. In other words, all the partial derivatives of h with respect to each of these components, and then I'm going to multiply it by j. And if you write this out, you'll see that I get, this is a very compact way of simply writing these two equations. Okay, and similarly with a z dot, where I'm going to have j multiplying the gradient of k with respect to my new variables. Any questions there? Is that okay? Okay, so that's what I have then, and just make sure we all have the same notation again. Here, the component of the gradient of h with respect to z, the jth component is simply dh dz, okay? And the same is true for k. So we now have a compact way of writing our decay equations of motion. We want to see how these two relate to each other, and the way we do that is we're going to say let m be the Jacobian of the transformation z as a function of z. So here, this expression basically is another way of simply writing this one up here for each of the variables. So this is basically z, the vector z, is equals to a function of the original vector z. And so the Jacobian associated with that transformation has m elements. It's a 2n by 2n matrix. It has elements partial zi, partial the small zj. Okay, so that's just our transformation matrix. The transformation is well defined if the determinant of that matrix is non-zero. Okay. And so if we now try and write out what z dot is, big Z dot is, in terms of little z dot, we can simply say big Z dot I, in other words, the tau derivative of the ith component is simply the partial of zi with respect to little zj summed over j, so it's for all the components of little zj times zj dot. Okay? And if you look at this carefully, this is exactly the definition of, you can rewrite this thing, if you put all the z's in your vector, then you have this derivative is simply the matrix and multiplied by the small z dot vector. Okay, so it's a very complicated, compact form of actually writing out how the transformation affects the equations of motion. So we now have that z dot transforms, and we want to see whether we can use this to get restrictions on the actual transformation itself. Okay, so what I'm going to do now, I want to keep this whole side on this right-hand side, but I want more space. So I'm going to move it all to this side and drop this first thing. But whatever you're going to see on the left now is going to be exactly the same. Okay, so there, I've just shifted what we had, so we can still use it. Okay, so we now have z dot, big Z dot in terms of m, little z dot. What we also have is we want to express dh dzi, we can also express it in terms of our Hamiltonian but in the other variables. So we have dh dzi is equals to, remember k is a function of your big coordinates, so that's simply dk d big zj then multiplied by d big Zj, d small zi. Okay, and we are summing over j. Okay, so that's your how we can express this Hamiltonian's derivative with respect to a single component Zi in terms of the derivative of this k with which has the same value but is expressed in terms of the new coordinates big Zj. And so we have that expression, and once again we can replace this partial Zj, partial little zi, with this thing. Okay, so you can see from the definition of m, the order's been switched, so simply the transpose of m multiplied by the gradient of k with respect to z is equals to the gradient of h with respect to little z. Okay, if you don't see this thing immediately, take the 2 by 2 example, write it out, and make sure it works, because it's a very powerful thing that you're going to encounter again later on, or this type of change of variable you're going to encounter again several times. Okay, so we now have the gradient of h with respect to little z is simply equals to mt times the gradient of k with respect to z, big Z, and what we can do is we can now go back to the equations of motion and see what that means for the actual transformation. So we can basically say, let's go to the equations of motion, namely these two down here, and we can replace both z dot and big Z dot in this equation which we derived at the bottom, simply by looking at how the time derivative or the parameter time derivative transforms. And so we're simply going to replace z dot with j, the gradient with respect to big Z of k, and little z dot with j times the gradient of little with respect to little z of h. And so what we then get is this expression. We can go further and we can then replace this gradient with respect to little z of h with this, the way it transforms in terms of k. Okay, so I've basically replaced this guy over here with that guy over there, and so I have mjmt times the gradient of z of k equals to j times the gradient with respect to big Z of k. And what we now want to do is we want this transformation, we want to find the most general rules of the transformations that does this, and we want them, the rules, to be valid for all k and h. Okay, and so clearly if k is arbitrary, the gradient of k with respect to z is also arbitrary, so the criterion we need to actually have the restricted generalized canonical transformation is simply that j must be equals to mj times mt. So we now, and that's basically what we call a canonical transformation, and if you look at it carefully, remember m is just the derivatives, the partial derivatives of the transformation itself. So we've got a highly non-trivial condition on the derivatives of these two n equations. Okay, and for now, that's what I'm going to call, that's the condition that we have a canonical transformation. And I'm going to define, it's basically the definition of M. If you have a matrix that obeys this thing, it's known as a symplectic matrix. Okay. So now we have a canonical transformation, and what you can rightly say is, well, it's great, we have a mathematical definition. It's not useful. How do you find M? And what I'm going to do now is first show you the power of it, and the next time I'm going to start looking at strategies for finding M. And that's the strategy that I actually realized I missed possibly for looking at trying to solve the problem we looked at, which is actually good news because it gives another way of going forward. Okay, so we now have that if you have a symplectic matrix M, that is basically, or is your Jacobian of the transformation. In other words, Mij is partial Zi, partial little zj, then we have everything we need. We have a transformation that will preserve both the equations of motion, structure, and go to new variables. But we must obey this little thing. So rather, before I solve it, I simply want to look at some of the more of the consequences of how we can manipulate this expression to make it look in different ways. Because it's a complicated expression, we want to look at all its disguises so that when we prove theorems, it's useful. So the first thing to observe is that I can multiply this side on the right-hand side, I can multiply it on the right-hand side by the inverse of M transpose. So I can multiply this, and then that disappears, so you're left with Mj. But then you have to multiply this on the right by the inverse of M transpose. So that's how this identity is obtained. And you can switch the operations of inverse and transpose, so this is also true. Okay, and then you can once again go and you can multiply both this side and that equation by m minus 1, so you're left with j m minus 1. Sorry, j is equals to m minus 1 j m minus 1 t. Okay, so what that means is if m is symplectic, then so is its inverse. The next thing that's useful is if you have j squared is equals to minus the identity matrix. Okay, right, and that you get by simply multiplying out these two matrices, and you can see that you're going to end up with a whole bunch of minus ones on the diagonal if you do that. Okay, and that's useful because you can now go and you can say, once again, take this expression mj, multiply it by j in front, so you have j mj is equal to j squared times mt to the minus 1, which is simply minus mt to the minus 1. And you can then multiply on the right-hand side by j, so there and there. So this is again minus 1. And what you're then left with is jm equals to mt to the minus 1 times j. And you simply have that your mtj m is equal to j, which is this expression except that the transpose has then moved. So it's a sort of a symmetry in your expression. So whether you work with the Jacobian or its transpose, you're still going to have the same identity. So if you've made a mistake in the way you label these indexes, your canonical or your symplectic condition is still the same. Okay, so those are little tricks that I'm going to need to manipulate what comes. And what I now want to do is I want to move on to the Poisson brackets. So I introduced those Poisson brackets for a reason. Let's see what it means with respect to a canonical transformation. And the first thing we're going to observe, which I didn't put in the first lecture, is when we define our Poisson brackets, we have basically derivatives in the definition with respect to the conjugate coordinates and the conjugate momenta. Okay, so as a first guess, you would think your Poisson brackets actually might depend on the way you choose your coordinates because it's in the definition. Okay, and so just to make it apparent, because I'm going to be looking at Poisson brackets in different coordinates, I am going to put a Q and P at the bottom here. So it's basically going to tell you what I'm taking the derivative of my dependent functions G and H with. Okay, so that's just a little bit of additional notation. I'm also going to be able to write this thing as, instead of writing PQ, I'm also going to indicate exactly the same thing if I put a Z there, because Z is my vector that combines both P and Q together. Okay, and if I now look at this definition, you can say, okay, I can actually write this definition out simply by saying it's the gradient of G, okay, transpose multiplied by J times the gradient of H with respect to Z, okay? And I'm going to tell you, and you can verify it on your own, that in fact, if you were to write this whole thing out, you would simply get exactly that definition. Okay, so it just makes it easier for me to actually derive things if I'm working with this, that I know how it transforms, rather than with my original definition, but these are entirely equivalent. And what I'm now going to do is, we've seen the Poisson bracket works when we work out the equations of motion, but let's just play a more general game. Let's explore what the Poisson bracket does for if we choose G and H to be our canonical variables, in other words, P and Q, okay? Because if we know what the Poisson brackets of P and Q is, in principle, we can work out the Poisson bracket of any function of other variables as well. So the first things you have is if you have two Q's and you work out their Poisson brackets, it's always 0. If you have two P's and you work out their Poisson brackets, it's always 0, because, remember, dP dQ is 0, right? And dQ dP is 0 because we're considering to be independent variables. So one of these guys is always going to vanish, and so it's 0. So strictly from the definition, you simply have that. The second thing you have is the Poisson bracket of Qj and Pj is 0 if, there's a mistake here, J is not equals to K, okay, so that I should be a K, and it's equals to, and that's equals to minus the Poisson bracket of Pj Qk, right? I've just switched the order, and that's also equals to the delta function of, or the Dirac delta function of Jk. Okay, so that's useful. In other words, so only when your variables in some sense cross over do you actually get ones. For the rest you have zeros. And if I now go on, just for references of notation, people call these the fundamental Poisson brackets. In other words, the Poisson brackets of the variables you're actually considering. Okay. And one way of summarizing the fundamental Poisson brackets is to put them all in a matrix, basically make a matrix of all the possible Poisson brackets you can have, and that matrix we are going to call the square matrix Poisson bracket. In other words, it's a thing I denote in this way. It's a Poisson bracket of Z, which is a vector with Z, and what that is simply says the Lmth element of this square matrix is simply the Poisson bracket of Z, L with Zn. Okay? And we can obviously work that out. We've got all the details up here of how to do that. And if you then do it simply by using these definitions, you're going to see that the square matrix Poisson bracket of Z with respect to Z, in other words, your coordinates, your canonical variables are the small ones, is simply J. Okay, so all this notation is simply summarized in this expression. So now we can go on and we can say, okay, we know we've got other functions, and those functions of P and little p and q are our big ones. So let's work out what the Poisson brackets are of the new variables. And it's still going to be derivatives with respect to the old ones. So what we're now going to do is we're going to say, if G and H are our transform variables, in other words, we are going to pick one of those transformations for P and Q, let's work out their Poisson brackets. Okay, so we want to work out the square matrix Poisson bracket of the new variables with respect to the old ones. And so to do that, what we're going to do is simply work out the elements. So we're going to take one new variable, ZL, work out its Poisson subbracket Z of Zm with respect to Z, and to do that, we're going to go back to our simply rewriting of this Poisson bracket in terms of this vector form. So we're simply going to have, it's the gradient of Z of big ZL, basically the row vector, times J, which is that matrix that we just defined earlier with zero matrices in the diagonal, and then identity and minus identity on the off diagonal shoots. Okay, and it's simply J times the gradient of Z with respect to the gradient with respect to little z of Zn. And now what we're going to say is, okay, we can simply write this, and we can use the definitions of what these things are, which is exactly the same as how we actually defined our Jacobian. So if you look very carefully, this gradient of Z, big Zm with respect to Z, okay, if you do it for all the components, it's simply this Jacobian matrix. And if you work out the transpose, it's simply this other Jacobian matrix. Once again, if you don't see it quickly, write the thing out and check it. Okay, so simply from this expression and what our definition of the Jacobian is, we can then simply replace this gradient Z of Zm for all the m's with respect to our Jacobian matrix, and this one that's just a transpose with respect to mt. So what we now have is, for our new variables, our transformed variables, we have that the Poisson bracket of the new variables is z comma z, the square one, basically summarizing everything we have, is simply mtjm. Familiar? And so I've not yet said anything about the transformation. I simply used the variables. If the transformation was canonical, in other words, this thing was symplectic, that mtjm was equals to j, then we simply have that our Poisson bracket is this. Okay, so this is true for any arbitrary transformation. If we then put the restriction that the transformation is canonical, then the symplectic condition holds, and you have the Poisson brackets, the square matrix Poisson bracket of the new variables equals to mtjm, which is equals to j. And you can do the reverse as well, okay, because there's nothing special we did about the derivation. If you can show that the transformed variable's square Poisson bracket is equals to j, you know by simply working it out that then the symplectic condition holds, right? Because you've proven that that's always equal to mtjm, and if it's equals to j, then the transformation is canonical. So it goes both ways. And so the equivalent of saying you have a canonical transformation is that basically the Poisson bracket of your canonical variables is equals to j. Okay, so now important is, or rather first observation is, it doesn't matter whether you working in the new variables or in fact in the old variables, the Poisson bracket of your variables is always j. Okay, now what I'm going to do is switch. I'm going to say, instead of taking my derivatives with respect to little q and little p, I'm going to take them with respect to big Q and big P. Okay? And so now I'm going to say at the bottom here, I'm going to say, basically indicate which canonical variables, the new variables that I'm now taking the derivatives with respect to, and I'm simply going to say this Poisson bracket is equals to of two functions is simply equals to the same structure, but the derivatives are now with respect to the new coordinates. And so what I'm then going to get is simply express it again. I'm going to give it that notation, and I'm going to say it's equal to this now that you have, but now you have gradients with respect to the big coordinates. And so if I do that, I immediately have, by exactly the same arguments, that the square matrix Poisson bracket of your new variables with respect to the new variables is equals to j. So at least for your variables, it doesn't appear to make a difference if you work out this entity with respect to which coordinates you're taking it. Whether you're taking it with respect to your new coordinates, the z, or in fact, if it's a canonical transformation, whether you took it to the old coordinates. And that's the power of the Poisson bracket. The things that you work out with it are in fact, and I'll show this more detailed now, not dependent on which set of canonical variables you're working with. Okay, so you basically have this, the Poisson bracket with respect to the new variables is equals to j, which is equals to the Poisson bracket with respect to the old variables. And so then you have a result, the fundamental Poisson brackets are invariant under canonical transformations. Okay, and this is why when I introduced it right at the start, I didn't actually put on these q's and p's at the bottom of the bracket, because it didn't matter when I computed this entity whether it was with which variables. As long as they're canonical, I was taking the derivative of. Okay, so it is one example of how you compute invariance or quantities that are invariant under the actual transformation of your coordinates. And it's a powerful tool when you do physics. Okay, so what you have is this Poincare invariance is basically equivalent both ways to the symplectic transformation, sorry, for the symplectic condition of your canonical transformation. So the problem is that you're going to see this is why I'm actually giving you all of them. You're going to see, when you read the literature, you're going to see people talk about this thing in different ways, and I want you to know exactly that how they translate between the two. It depends in how the person was trained, what notation he's going to use when he actually talks in a paper about it. And I want you to actually, you don't have to remember everything precisely, you just need to go and know where to go and look to actually know how these things communicate with each other. Okay, so Poincare invariance implies the symplectic condition, which is also equivalent to having a canonical transformation. Okay, and now you have the major result, which is why Poincare brackets are so useful. You can say all Poincare brackets are invariant under canonical transformations, not just the fundamental ones. And the way you prove that is simply saying, let's consider the Poincare bracket of G and H with respect to Z, so our PQ, our initial variables. We're going to then express the derivatives with respect to Z in terms of the partial derivatives with respect to big Z. So this is in some sense just systematizing some of the things I've already said. Okay, so we're going to have the gradient of H is equals to MT, the gradient of H with respect to Z. And you're also going to have the transfer version of true being true, namely the gradient of G with respect to Z transpose is then just the gradient of Z with respect to G transpose times M. Okay, so you have those two things. Then you can simply write out the Poisson bracket as the Poisson bracket of GH with respect to Z is simply by definition the gradient of G with respect to Z transpose times J times the gradient of H with respect to little z. And then you use these definitions, those two, okay, to simply replace the derivatives with respect to little z down here with a transformed version, in other words, the derivatives with respect to big Z. You once again see this symplectic condition coming through, and you have that if the transformation is canonical, this thing is simply equals to J, And you then have this Poisson bracket of G and H that are functions of little z. The derivatives taken with respect to little z is equals to this, and sorry, I'm missing an H over there. And that's equals to the Poisson bracket with respect to big Z. So there I've rigorously proved every single Poisson bracket. It doesn't matter whether you've expressed your functions with respect to little variables or the new variables. If you work out that Poisson bracket, you're going to get something that's not dependent on it, which is very, very nice. Okay. And basically all Poisson brackets are canonical invariants, and therefore I basically drop the subscript from now on as to which Poisson bracket I'm working with, how I'm taking the derivatives, and I'm assuming that I'm only using canonical coordinates. In other words, coordinates that have equations of motion that obey that Hamiltonian structure. Okay, so that's very powerful. And so to end today, what I'm going to do is I'm going to give you a number more properties of the Poisson bracket itself. Because when they developed quantum mechanics, it was a mishmash between looking at that experiment, getting equations to try and describe what they were seeing with the particle collisions and their chemical experiments. And the people that knew that were very fit with classical mechanics, because at that point that was the only thing it had. You had less knowledge, both mathematicians and physicists, at the beginning of this century. If you go back into Cambridge and you look at the exams of what they were writing, they are of a tremendously high standard, and they were all very fit with classical mechanics. So when quantum mechanics and relativity were born, you had a whole population of people that are way fitter, to be honest, with this type of thinking than what we are now. Okay. But that's okay. Knowledge goes on, but it is sometimes useful to make sure, in some sense, the canon where you're starting from is well established. So let me give you some properties of the Poisson brackets that then actually makes the connection with mathematics, right? And in fact, it begins to explain why so many structures are actually seen in physical systems, and why later on a lot of mathematics now connects group theory very strongly with things that we see. And it starts here, because the Poisson brackets actually, if you abstract them away from being the way you define the derivatives of the Hamiltonian and the way that evolves, they have a structure on their own. And that's what then was generalized into quantum mechanics. So what you have now is simply some algebraic properties of Poisson brackets. For our purposes, it's going to be useful because it's going to make other calculations easier, and it's just going to get you more of a feel. So many of these you've actually seen in the proofs. The first one is antisymmetry, basically meaning that Poisson bracket with itself is 0, which you saw. But also this other one that you already saw when I looked at the fundamental Poisson brackets, namely that the Poisson bracket of G and H is equals to minus the Poisson bracket of H and G. Linearity, so feels like I'm giving an algebra course. Basically, if A and B are constant, then the Poisson bracket of AG plus BH with K is A times GK plus B times HK. The product rule, right, because we want to look at the product once we've gone past the fundamental brackets, the most simplest thing is simply the product rule. And you can in some sense see that this is inherited because it's made with partial derivatives. That's where it comes from. So the Poisson bracket of GK comma H is G Poisson bracket with H times K plus K's Poisson bracket with H times G. Okay? And the final one is the Jacobi identity. This one is harder to prove. You can still get it by simply writing out the definition of the Poisson brackets and very cleverly combining it. And it is actually given in Goldstein. So if you want the proof, I don't do it here because it's tedious. But what the Jacobi identity is if you have G, K, and G, H, and K that have continuous second derivatives, so functions of whatever canonical variable you're working in, then you have this combination. You have the Poisson brackets of G with the Poisson brackets of HK plus, okay, and see what I'm going to do. I'm going to take this K, I'm going to switch it around to the position of G, and then I'm going to move the next two on. So I'm going to move GH on, okay, plus that Poisson bracket, plus I'm again going to take H, put it into K's position, and then move the next two on. HKG is equals to 0. So if you write that out, want to say it, it's basically the sum of the cyclic permutations of your double Poisson bracket of three functions is 0. Cyclic permutations meaning that I retain this order. In other words, GHK, and I retain GHK and GHK. I retain that order. That's 0. And that's the powerful identity that's hidden in the Poisson brackets. And that thing, the second identity, makes, okay, so that's where the proof is, if you want to go and check it. These three identities, asymmetry, linearity, and the Jacobi identity, are what you need if you start working with non-associative algebras. Okay, so those three identities make the Poisson bracket a Lie algebra. Okay, so all the results, a Lie algebra. All the results, I'm not lying, but the guy's name is Lie actually. All the results that you have from the algebras, all those identities, all the algebras that have been studied are eventually applicable to Poisson. Poisson brackets fall into that category. So, and so what happened when they went from classical mechanics to quantum mechanics, they kept everything, almost everything in classical mechanics of how the Poisson brackets work. If they simply took classical mechanics and they took all the results and they replaced the Poisson brackets with another structure, an operator structure, that was also in the algebra, then a lot of the results can be mapped one-to-one. Okay. And then they went on from your Lie algebra and used those results to say other things. So that's how, in some sense, a birthing of quantum mechanics came from classical mechanics. Okay. So that's basically where I'm going to stop today. What I'm going to do the next time is lots of nice abstract theory we want to calculate. I'm going to actually look at techniques of how you actually... So this is a condition on the partial derivatives of those transformations. It's a very hard condition to invert. In other words, to actually find the transformation that's going to do it. And I'm going to start looking at strategies that actually can do that. Okay. And that then goes on to the KAM theorem. But I just sort of wanted to give you the idea that when people invented quantum mechanics that they taught you within the first year, it wasn't random. It wasn't the way it's taught. It was a very logical progression from quantum mechanics, and it stuck very rigorously with the mathematical structures which Jacobi and Hamilton a century before had very neatly categorized. Like when Hamilton went and said, look, we've got all these systems, we can all express all the equations of motion in the right coordinates in terms of these Poisson brackets, and they all have the same structure. That was necessary for people to actually go in and develop quantum mechanics. The other interesting things, which is in Goldstein, the first couple of chapters of Goldstein, he doesn't start with the Poisson brackets like I did. I simply did that out of expedience because I wanted to get you calculating in Hamiltonian dynamics as quickly as possible. So it basically became this game that we can play. If you look at how Goldstein starts, he uses calculus of variations. And you can show that way of thinking can be transformed directly into this Poisson bracket Hamiltonian dynamics things. What the people that developed relativity did is they used that side. So that's more natural when you think about space-time, the idea of paths that Jacobi developed to describe classical mechanics before Hamilton came down, or Lagrange and them, before Hamilton came along and said we can write it this way. That is the way that the relativists went and then got generalized into GR. So in some sense you had a split where the two branches, the one was suitable for generalizing to quantum mechanics, the other one suitable, the way of thinking about it was generalized to GR, but for classical mechanics the two are exactly the same. There's one quantum correspondence. So that's all for me for today. I'll tell you next time. I will talk about the how we actually start looking for transformations that are useful rather than just abstract theory, and then we can start doing it on the curve first, and then hopefully on more, because I now have a new way of trying to go for more. So that's it for me.